All good? All ready for the weekend? What a long week. Felt like yesterday was Friday. All right. Well, anyway, we talked about binomial distribution last time, so let's do a couple more problems, and then we'll do a couple of other distributions today, one of which we've already talked about some. So let's look at this next problem in the homework, the problems packet that I gave you last time. So we've got an airline company sells tickets for a small plane. So 32 tickets for a small plane. They tell you that the probability that any particular passenger will not show up for a flight is 0.1, and that it's the same for every single passenger, and one passenger not showing up doesn't influence any other passenger not showing up. So we want to calculate the probability that there are more passengers show up for the flight than there are seats, right? So this is probably a binomial problem. Otherwise, it's a really badly chosen example by me to illustrate what's going on, right? So remember, binomial counts number of successes, right, in a certain number of trials. Okay. Pardon me. So in this case, how many trials are there? 32. There's 32, right? Because there's 32 passengers, and we're looking at whether or not a particular passenger shows up or not, right? So we've got each passenger would be an individual trial. So there's 32 trials in this case. How are we going to define success, do you think, in this case? Not showing up, since they give us the probability that it's not showing up, right? And in that case, your P will be 0.1. By the way, you could also define your your success as showing up, and then your P would be what? 0.9. Yeah, you can do it the other way around too and get the same answer. Yeah, as long as yes.
You always miss on that one out given to decide the probability.
Well, the probability has to be given to you somewhere, right? They have to tell you. It depends on the situation. In this case, they tell you it's 0.1. So we might as well use that for the probability of success. But again, we could use 0.9 if you want to flip the problem around. It's your choice. You just need to make sure that if you flip the success around, then you're going to be counting something else, right? If we're going to count this in this case, we want the probability that more passengers show up than there are seats available. So if we define success as not showing up, what do we need to calculate the probabilities for if they're going to, basically the flight's going to be over? So what does the X need to be in this case? 31, 32. So we defined success as
0 or 1.
0 or 1. Yeah, we flipped it the other way around, right? We defined the success as not showing up, right? So in order not to be oversold, we would need 2 or more successes. This is asking us for the probability that the flight's oversold, right? All right, Emily, I think you can I gave her yours. There we go. I flipped it. Sorry. That's my bad. All right. So this problem's asking us for the probability that X equals 0, 32 people showed up, or the probability that X is equal to 1. We can add them together because they're mutually exclusive events, right? We want X is 0 or X is 1. What would you get for the probability that X is 0?
Choose 0.
Okay, so the 1 minus p in this case is 0.9 to the, which is 32, and 0.1 to the 0 in this case, right? Say that again. What's your PMF for the binomial? What's the PMF for the binomial distribution? What's the PMF? Just generally, what is it? It's on that sheet next to you too. If you flip it over. It's that n choose x, right? And p to the x, 1 minus p to the n minus x. That's where those things are coming from. Here's your n choose x. There's your p to the x, and there's your, it's written flip-flop, but this is your p to the x, and that's your 1 minus p to the n minus x. That's where those are all coming from. That's for 0. What do you get for 1 then? Good. Oops. Start writing my 31 instead of my right parenthesis. Yep, there you go. Notice that you could do this, if you're using your calculator to get a final answer, you could do it in several ways. You could type in everything you see here, or you could get rid of the ones that have the zeros in it, because those are going to be 1. But you can type in everything you see here to get an answer. You could use your binomial PDF function in your calculator and calculate each of those individually and add them together. Or you could also use your binomial CDF function, because x equal to 0 plus x equal to 1, those probabilities, that's the same thing as the probability that x is less than or equal to 1, and that's exactly how the CDF is set up, right? So you could do that as well. So you could put it in one function in your calculator if you were trying to get to a final answer. If you defined it the other way, if we said that x counts number of passengers who show up, flip your what you mean by success. Brain stalled for a second. Flip what you mean by success, rather than in this part up here in this solution, we define success as not showing up. If we flip it, n is still 32, but what's p now? It's 0.9. That's the probability an individual passenger shows up. What probabilities would you want to compute in that case? Yeah, x equals 31 and x equals 32. Good. All right? And so you plug it into your formula. Notice that this is the probability that x is greater than or equal to 31, right? It's 31 or 32. The reason why I'm mentioning this, can you convert this into a statement about the CDF? What would I do to rewrite this so that I see something about the CDF? Probably that x is less than or equal to, it's going to be 30 in this discrete case, right? Because we don't want to include the 31, and since it's discrete, we'll drop down to 30. So now you can do this in terms of the CDF. The reason why I wanted to do this is because when we get to continuous distributions later, we're going to calculate a lot of things using the CDF rather than the PDF, because, well, some things I should say, not necessarily a lot of things. Because when we do probabilities in continuous distributions, we're going to do integration. So it's going to be adding across a continuous interval. If we have the CDF, we've already done the integration in advance, so we can just plug the number in. So in a lot of problems, it's going to be beneficial to you to be able to rewrite the probability you're trying to compute in terms of the probability for the CDF. It's the only reason why I mentioned this. You don't have to do this way. All right. Just as a precursor for something that's coming in the next chapter. That you're very excited about it. Yes. Remember that we define success as not showing up. We want more than 30 to show up. So we need either nobody didn't show up, so they all showed up. That's x equal to 0, or only one person didn't show up. And so then we had 31 people try to get on the plane. That's why we did that in the first one. Because our success in the first one, x is counting. X counts the number who don't show up. That was why it was different. Other questions on that one? All right. Let's do this one and see if we can think about how we could do this. Think about it for a minute and then we'll chat. Ready to chat about it? It's all very quiet. Very unsettling. All right. So let's just call the random variables associated with coin K and coin L K and L, what is it you're trying to figure out the probability for? What does K have to be and what does L have to be? Yeah, exactly 3 and exactly 6. Good, that's exactly right. We want the probability that K is 3 and L is 6, right? Now, what do we know about the tosses for all of the coins? They're independent. So since they're independent, how can we break that probability up? Good, exactly right? We can break it up as a product, correct? Cool. All right, so I just wanted to remind about the independence here, right? We really are trying to figure out an and probability. We're told that all the tosses are independent regardless of which coin you're using. So the probability and is going to be the product of the probabilities. What can you say about each of your random variables? We want exactly 3 heads for K. Are the tosses independent? Are the probabilities of flipping a head the same every single toss? Yeah, so only 0.3, right? Okay. So that's binomial, isn't it? Right? We've got independent and identical trials, and we're counting successes. What is success in this case? Head. So your P is going to be 0.3 for K, right? So this probability right here, the one that I just underlined-ish, it was supposed to be a brace. We'll just pretend like it's a brace. What's that one going to be?
5 choose 3. 0.7 squared.
Okay. Is that what others got for that one? Okay. And then for your other coin, your P is what? Your probability of success is what? 0.1. So what's the other one going to be? Okay, good. So yeah, the failure will be 0.9. So then your what's your probability that it's equal to 6 going to be? Good. Good. Whatever that turns out to be. Is that okay? We're also very happy about it. All right, let's look at one more. I'm going to skip the next one. We're going to skip the next one. Well, I'm going, let's briefly stop at the next one here. Not go through all the computations. Percentage of college students who have engaged in binge drinking. Yippee. All right. What amuses me is, this is just a side note. It has nothing to do with class at all. What amuses me is the author of the original textbook, one of the authors, Hogue, was a professor at Iowa. I went to Iowa. The weekend started on Tuesday. We'll leave it at that. Okay. All right. I went to Iowa for grad school. The weekend started on Tuesday, definitely. All right, anyway. I just think it's funny they have a binge drinking question in the book and stuff, given the environment that I experienced at Iowa. All right, anyway. We've got percentage of students was 40%, and then the X equal the number of students in a random sample who binge drink. All right. So which of the, of A, B, and C, which of the questions is a PMF question? A single PMF question, because it should be answered by directly plugging in one number into your PMF. Which of those, A, B, or C is? C, right? Because it says is equal to 7, right? The only reason why I'm mentioning this is because of stuff that's going to come up later when we start switching over to continuous. This is a PMF question, right? You agree? The other ones can be written in terms of your CDF, right? We agree? So this is probability that X equals 7. This one, part A, I believe is directly a CDF question, isn't it? It says the probability of that X is at most 5. We agree? Okay. So this would be directly a CDF question. It's probability that X is less than or equal to 5. if you had the CDF already computed, and in a lot of cases, or at least in a couple of special cases, I guess I should say, in the continuous distributions, you will have a CDF that you'll know. And so you can just plug in the value into the CDF if it's in this form. Okay. So this is a CDF question. Is B a CDF question? The way it's written, is it a CDF question? No. Can you convert it to a CDF question? Yeah, so you can convert it to the CDF, right? What does part B ask you for the probability? It's the probability that X is greater than or equal to 6. If you want to convert it into a statement that involves the CDF, that's the same thing as good. Yep. 1 minus the probability that X is less than or equal to 5. That's exactly right. Good. The reason why I'm harping on this a little bit is later on we're going to talk about a couple of special types of distributions. One is what's referred to as the exponential distribution. Pardon me. The exponential distribution has a nice, straightforward formula for the CDF. So if we can write things in terms of the CDF, we can just plug the numbers into it and we're done. Right? The other very, very, very important distribution we're going to talk about is the normal distribution. If you've done anything with statistics at all, you've probably seen a normal distribution table, right? We will have a slightly different version of a normal distribution table. I think this book uses slightly different that involves the CDF. And so when we do the normal distribution, we're going to want to convert our problems to normal CDF and then use the table. Or your calculator also has a CDF built in, right? So you can use those as well to help you out. That's why I'm making a big deal out of it now, because it's stuff that's coming up later. The last little big deal I want to make out of this is, let's see if we remember our mean and our variance for a binomial. Right? We collected those the other day. This is a binomial distribution. How do we find the mean again, generally? NP. In this particular problem, your N is, and your P is 0.4. So it looks like we get 4.8. Variance is what? NPQ. Q in this case is 0.6. Oh, goodness. What do we get? 2.88? Did I do that right? 24 and 4.8. Oh, wait. That's right. And then a 6. Yep, I think that's right. Feels right. Thanks, Trace. Was that it? Yeah. Yeah, I did. It wasn't too bad because I already did the n times p above it, right? So I did 6 times 4 is 24, and 6 times 8 is 48. So I just did 24 plus 4.8 and move my decimal place one place over. Obviously, of course I did. You got to remember, when I grew up, I didn't have a calculator until I was a junior in high school. So a lot of things had to be done by hand, and it's all stuck. And I've been doing math for a long time. Well, let's see. Let's see. This is number 19 years here, and I taught 8 years before I came here, and I did 5 years of graduate school and 4 years of undergraduate. I don't want to add that together. It's a long time. So anyway, yeah. Anyway, then the last one here, how you do standard deviation. Just do the square root, and I'm not doing the square root in my head. I know, it's disappointing. I can probably get a pretty good estimate of it, though. What is that, 1.2 square root of 2? This is 1.44 times 2, isn't it? Underneath the radical? And the square root of 1.44 would be 1.2, because it's square root of 144 is 12, right? So square root of 2 is about 1.4. If I want to multiply 12 and 14 together, we get 168. So it's about 1.68. Yeah. So see, I was going to guess it should be a little bit bigger than 1.68 because the square root of 2 is 1.414 and change. So what? What? You're all looking at me like I'm crazy. Anyway, one of the favorite things in one of the things back when I was a junior in high school, I didn't pay attention a lot in class because I knew what was going on, right? So I'm doing other things. There was a student teacher, or a student teacher, was in there teaching the college or the algebra 2 class. I'm not paying attention, but I know what's going on because we're simplifying radicals. She did not like the fact that I was not paying attention. So she literally called me out. What is this? And I just told her, and I went back to what I was doing. She was not very happy with me. She asked, I looked up, I told her, and I went back to whatever else I was doing because I wasn't paying any attention. It was rewriting cube root of 40. I actually remember what it was. But it has an 8 and a 5 in it. It wasn't that hard. 2 cube root of 5. Went back to what I was doing. I was a little bit of an ass. It's fine. Still am. Just ask Dr. Stickles. All right. Any questions on this one at all? All right. I do want to do one more. I forgot that I wanted to just remind about the CDF bit and do the not that one. Where is it? There it is. I wanted to remind about the mean and the variance for the binomial distribution. Another reason why I wanted to do that one. Let's do this one. This one's got some binomial things in it, but it's also got a Bayes thing in it. So I want to go back and look at it. So, got a hospital receives flu vaccines from 3 different companies. Looks like company B is a little bit more reliable in their vaccine than the other 2 companies. Hospital is going to test 5 vials. If at least one is ineffective, we want to find the probability that it came from C. So again, just writing down the conditional here, we want the probability that it came from company C given at least one ineffective. Right, that's the probability that we're looking for. The reason why this is a Bayes problem is if we look at the setup of the problem, we're given probabilities of being ineffective from the different companies, right? So if we knew the company, calculating the probability that it's ineffective is pretty straightforward, right? This is asking us, given that it's ineffective, is it from C, right? So we need to flip it around, okay? Flip it around to what we're given. So remember again, with our conditional probability formula, what goes on top? Just generally speaking, with our conditional probability formula. Yeah, the intersection part, right? So it's the and part, right? So it's C and 1. I'm just going to write 1 ineffective, but remember we need to do at least 1 ineffective, right? I just don't feel like writing a lot of letters. And then what goes on bottom? Yeah. Oh, actually, you know what? I'll just put a greater than or equal to sign in front of my 1. Okay. All right. And so then this will be where we flip things around, right? On top, how can you rewrite the top as a different conditional?
EFC times the probability of at least one ineffective given C.
Good. That flips it around, right? And this is, we can compute this, can't we? Because if we know it comes from C, we should be able to figure out the probability that there's one ineffective. Now the denominator we're going to have to split into pieces, right? To get to one ineffective, we've got three different choices of companies we could have gone through, right? It could have come from company A. It could have come from company B. It could have come from company C. So on bottom, we'll split that into it came from A and there was one ineffective. Oops, given. Forgot my given. Or it came from B and there's one ineffective. Or it came from C and there's one ineffective. This should remind you of problems we've done before, I hope. Okay. Part of this we should be able to figure out pretty quickly. What is the probability that the shipment came from company C? 0.1? Yeah, Matt.
For one of the first two, is it given A?
Oh, it should be B. Thank you. I saw it as soon as you started asking the question. I looked over and I saw it. Sorry about that. And then from A, it's 0.4. Is that right? And B, it was 0.5, or do I have it backward?
Yeah.
Okay. Okay. All right. So I can fill in each of those individual probabilities by what they gave to us. None of that was new to this section, right? Bayes' theorem was old. They told us what the probabilities were. Okay. So the new stuff, this next part must be the binomial part, right? We know that if it comes from A, we are testing 5 vials. And we want to know if at least one of them is ineffective. Well, again, in this case, at least one would mean 1 or 2 or 3 or 4 or 5. That seems harder to compute. What should we compute instead? Yeah, 1 minus x equals 0, right? So let's do 1 minus for each of these. All right, coming from C, let's do the numerator first. Coming from C, we want no ineffective vials out of the 5, right? So what are we going to put in there? Good. You see a 0.95 to the 5th on that one? We want no ineffective vials. If it comes from company A, what's the probability that it is ineffective? The 0.05, right? And so we're doing no ineffective vials. So the 0.9, we want all 5 to be effective. That's why it's 0.95. What do we get? So that's the same thing that's down here. What's the probability going to go for A? And for B? 0.98 to the 5th. Yep, good. It's a little bit hidden since I didn't write the other pieces in here, but this would be 520 and 0.05 to the 0 here if we were going to write out the binomial PMF, right? 520.03 to the 0, sorry, and 520 and 0.02 to the 0. We go in there. Going okay? Was it good we did a reminder of Bayes' theorem? No? Sorry. Yes. Okay. So I'll just write this one in. I'd have a 5, choose 0, right? Because we're choosing 5 vials, right? And then this would be a 0.05 to the 0. The other ones would look like that too, just for the different numbers. All right. All right. You all look sufficiently bored with the binomial, so let's change the gears. I'll leave the other ones for practice. All right. We've already talked about the hypergeometric. We'll just write it out a little bit more formally here in a second. So remember, for your hypergeometric, we split for your hypergeometric, you have a group of, I'll just call it little n objects split into 2 subgroups. And we'll use a capital N1. Oh, I'm sorry. I used a little n. I think your book uses a big N for the total number of objects. Yeah. They use a capital N for the total number of objects and a little n for the number that we're going to select. So, okay. All right. So a bigger group split into 2 smaller subgroups. So maybe you've got a group of people and split into freshmen and non-freshmen. That would be an example. A group of students, freshmen and non-freshmen. Okay, something like that. Just whatever you've got. You've got a large group. It's split into 2 different subgroups. Okay, group of students, athletes, non-athletes, something like that. Right? Okay, we're going to select. We select little n objects from the group, and our capital X, the random variable x, counts the number of objects, I'll just say of type N1, in the selection. Okay, so notice when I say I'm going to select n objects, I didn't say it explicitly, but as we're going to do this without replacement, we're going to take a whole group of them. So if I've got 100 students and I select, and say 20 of them are athletes and 80 of them are not, and I select 5, I'm just going to pull 5 students and say I'm going to count the number of athletes in that group of 5. That's what we need. So the selection here is going to be done without replacement. That's what makes it not binomial, by the way. Because once I pick an object, I can't pick it again. So the trials wouldn't be independent. Okay. Now, we've already said before that if your group is big enough, you might be able to go ahead and model this with a binomial instead. We've done that in a previous example, right? But we've already done problems like this, of course. Your PMF is, well, the denominator is that I'm selecting little n objects from the group of capital N, right? The bottom is just the number of ways that we choose little n objects from a group of big N. right? And we want x of type 1, and then the rest have to come from type 2. I have to be a little bit careful here. This isn't quite right, depending on your samples. What I mean by that is, if this number here isn't as big as what this number is here, I can't choose a negative number of things, right? So I may have to stop at some point. Okay, so this isn't, what I have double underlined over here isn't quite right. I know that my x can't be bigger than n, certainly, right? But your x also can't be, so let me actually just cross this out. Okay. Your x certainly has to be bigger than or equal to 0. I can't pick negative, right? It has to be less than or equal to n. But I also need what? X has to be less than or equal to n1. And we also need n minus x to be less than or equal to n2 for your support. It's more complicated than just saying from 0 to n. Rather than trying to memorize all that mess, just be careful, right? Just know that you cannot select more objects than what are available, right? Okay. All right. So the book goes through, and I don't think you have page numbers in your book, but if you go to section 2, if you look at your book, I'm not asking you to do that right this second, obviously. If you look at your book, somewhere near, well, little past halfway through the section's not very long at all. Little past halfway through the section, they go through and they compute the mean and the variance for the hypergeometric. Okay? It's lots of fun playing around with factorials. That's what I don't feel like doing today. You don't feel like doing it for certain. I don't feel like doing it either. Okay? So we're not going to do it. Well, let's see if we can reason through at least the mean. We should be able to figure out what the mean is, right? All right, so let's think about it for a second. If 20% of these objects are of type 1, so you had 20% of the objects are type 1, and you're going to select 10 of them, how many would you expect to select of type 1? If 20% of them are of type 1 and you select 10, how many would you expect there to be? 2. What'd you do? Just multiply it, right? Just kind of like we did with the binomial, correct? Okay? And that's exactly what happens. Your mean is just going to be the number you select, n, times capital N1 over capital N. That's exactly what your mean is going to be. This is just, this number right here is just the percentage of objects of type 1, isn't it? And you're trying to count how many are of type 1 in your sample. If this is the percentage of objects of type 1, you would expect n times that many to show up in your sample. Expected value, right? Mean, not guaranteed by any stretch. Now, for the variance, it's a little bit trickier, but part of it makes sense. The part of it that makes sense is, again, if your sample size, how many you're pulling out of the set, is really small relative to the size of all your objects, how big your group is, you might as well model with a binomial, right? If you've got 300,000 objects and you're picking 10, 1 out of 300,000 is just about the same as 1 out of 299,299, right? They're really, really close together, okay? What's your variance for the binomial? NPQ, right? So in this case, your N and your P is your percentage of the objects that would be of type 1. Your Q then would be the percentage of the objects of type 2. And this would give you a really, really good estimate of your variance if your group size was big relative to your sample size. Now, that doesn't always happen, right? Okay. So there is an extra factor that goes on the end here. And it turns out to be that. They go through in the book why that is the factor. Notice this factor is going to be less than 1, correct? So in general, your variance for your hypergeometric is smaller than your variance for the binomial. Okay? And that kind of makes sense, because if your sample size and your number of object size are getting closer together, there's going to be fewer variance in what you can pull out of the sample, right? Because you're doing it without replacement, right? You're not going to have as much variance in your chances. If you do it with replacement, then you've got the same opportunity to pick the same thing over and over and over again. It's going to change the variance. It's going to make it bigger, right? Because you've got more options. When you pick without replacement, the more you pick, the fewer options you have. It's not going to vary nearly as much. Okay, that's where this factor comes in. This is less than 1. But notice again, if your size of your group that you're choosing from is big relative to the number of objects you're picking, this is going to be really close to 1. Right? So again, if you've got 300,000 objects and you're picking 5, 299,995 over 299,999 is close to 1, right? Really close to 1. Okay. So that makes sense that this is less than 1, but as these numbers get really, this is big relative to that, that should get really, really close to 1, and you should get closer to a binomial. Again, like I said, no one wanted to go through and play with the factorials and get this thing to pop out at the end. Okay. All right, so let's see if we can do a couple of problems here with hypergeometric. Whoop. Yes? No, you have to memorize them. As a matter of fact, on the very first page of your next exam, there's going to be fill in the blanks of these things. That's what I gave you the sheet so you can memorize them. It's good for you. There's a reason why it's good for you. If you go take a certification exam, for example, you're not going to be given a sheet of formulas. You're going to have to know them, just as an example. So actuarial exams, for example, the only thing you get to go in is with a scientific calculator or a financial calculator, depending on the exam. So that's why I make you memorize them for the first time. I know, I'm mean. It happens. All right. You can always make note cards. Have the name of the distribution on it, and then you just say, okay, what is the PMF? What's the mean? What's the variance? What's the moment generating function? This one you're not going to have to know the moment generating function for, because it would be nasty. All right. Let's see if we can do a problem here. Six essay questions. Select 3 for the test. Student only has time to study for 3. What's the probability that, and then we got those other possibilities. So why is this hypergeometric? That's the first important thing that you do in any of these problems is, I need to figure out what distribution I'm supposed to use, right? And this is why I've been emphasizing what the variables count, right? And then when we get to continuous distributions, we're going to ask, what do they measure? Counting is a discrete idea, measuring is a continuous idea. Okay. So why is this hypergeometric? Do you have a big group of objects split into 2? Yep, I got a group of 6 essay questions. You got Group 1, the questions the student studied. Group 2, the questions that the student didn't study. Right? Agreed? Okay. So that's why it's high. And can the same essay question be selected multiple times for the test? No. So it's without replacement, right? That would be a nice essay exam, though, right? If there's a professor just put the same exam question on there 3 times. Just write ditto for the second one. All right. So this is why it's hypergeometric. So we want at least one selected. So in this case, X is counting the number of questions on the exam the student studied. Okay. We want the probability in the first case that X is greater than or equal to 1, right? That's at least 1. But let's see if we can identify the other parts so that we can plug this in now. Capital N, total number of objects is 6. Number of questions the student studied is 3, which also makes sure questions the student didn't study 3, right? How many questions are selected? 3. So your little n is also 3. There's lots of 3s here, right? But remember where each of the 3s come from. This is the studied questions, unstudied questions, questions that are actually selected. Okay. Well, in this particular case, since there's only 3 questions being selected, typically doing something greater than or equal to 1 would do, it's 1 or 2 or 3 and so on. It's usually hard to do, right? Usually if I see something like this, I want to convert it to the complement. This is 1 minus the probability that X is equal to 0. So in our PMF then, you told me that capital N1 was 3. We're choosing none of those. Oops, I forgot my 1 minus in front. Capital N2 is also 3. Just to write it in the PMF form, I'm going to write it as 3 minus 0. Because all of those are ones the student didn't study. And on bottom, it would be 6, choose 3. Is that 14 out of 15? Did you do that right? 19 out of 20. Oh, that is 20. Not bad. Thanks. I don't know why I did 5 times 3. It was 5 times 4. I can't do my factorial. Is that okay? Yes. No, it's exactly the same. We've studied the hypergeometric. We've studied it before. Yep. We're just, what we haven't talked about was the mean or the variance, right? But we've studied this before. You're right. It's not any different than what we did before. So let's do part C. What would exactly 2 selected look like? Good. 9 out of 20. Now that I figured out what the denominator is correctly. 3 choose 2 and 3 choose 1 are both 3, so it should be 9 out of 20. That okay? Let's do one more. I only have 4 on here anyway. Let's do 14. Only because it's asking you to do a little bit of a different thing. regardless of what the question's asking you, we should first decide what's telling us what type of distribution it is. This should be an example of a hypergeometric one. So it better be a hypergeometric distribution. So let's think about why this is hypergeometric. Do you have one large group of objects being split into two smaller groups of objects? Yes. Okay. Are we counting the number of one type of object in a sample? Yeah, we're counting the number of white marbles, right? Are we doing that without replacement? And that's also important, right? If it were with replacement, now you're doing binomial, right? Because your probability of success would not change. Okay? That's important that it says without replacement here. If it were with replacement, it would be a binomial question. Because you'd have a probability of success and a failure. That's why I said it's important to read the problem and make sure you understand why you're using one type of distribution over another. Okay. All right, so let's identify our pieces and then plug it into our formulas for expected value and variance. Capital N is 25. Capital N1 is 10. Good, because that's the N1 refers to the group that you want to count, right? So N2 is 15. Little n is 10. So just to label them, just make sure we're all on the same page. Total number of marbles. White marbles. And that's what we're counting. Right? The N2 refers to black marbles, but in general, that's the other group, right? Okay. And then the 10 is number of marbles selected. Just making sure we're all on the same page with what the different numbers are representing, especially since the two examples we've done so far have had repeated numbers, right? The first 10 has nothing to do with the second 10. Okay. All right. Using our formulas, what is the mean? Okay. Yep. So it's little n times capital N1 over n, right? Four. Your variance is what?
10 times 10 over 25 times 15 over 25 times 15 over 25.
Good. Remember, it's little n times N1 over capital N times N2 over capital N times capital N over minus little n over capital N minus 1. Do we get a value for that? So again? 1.5. 1.5, so it must be 3 halves. Is that okay? Notice that, again, this part right here would have been the variance for a binomial. Right? Since our number of objects in our selection is roughly, really roughly, half, right? Not quite half, it's a little bit less than half. It's split down to 5. Okay, but what is that, 2/5, 40%? Roughly 40% here. this, I've subtracted 1 off the bottom, but this is about 60%, right? So if the size is about 40% here, the variance went up, there's about 60% of the variance, because again, I can't pick the same object again, so my chances for varying aren't as good as if it were a binomial distribution. I got fewer choices. Finally, the problem asked for the variance over the expected value. So we would have 3 halves divided by 4, which would give you 3/8 as the final answer. This is what it asked for. Just to be a little bit more satisfying of actually finishing it off. That okay? Yeah, Declan.
Could you have simplified the formula of variance over the expected value of x, like just with, like symbolically?
Yes. Yes, you could have. Yeah, you could, and then just plug in the variance. Yep, you could have done that first. Yep, because the variance and expected value of x have in the little n and the capital N 1 over n of it. So you could have just chop those off to start with. Yes. All right, so let's start the new section. I'll leave those other couple of problems for practice. We've done, like I said, we've done hypergeometric before, right? These don't feel different than the types of problems we've already done, because they don't make it different, do they? Okay. All right, so let's do, well, actually, some other problems that like we've done before. We're just going to give a name to it. All right, so the next section that we're going to talk about is what's referred to as the negative binomial. But before we get to that, let's look at this first example. This has actually no, well, I guess technically it's a special case of what we're going to talk about here in a minute. But this should look like an example that we've already done. We have a multiple choice exam. Student has no idea what the answers are for the multiple choice exam, so they're just going to circle answers randomly along. This problem says, what's the probability that the first question answered correctly is the fourth question? What type of distribution is this? We've talked about this one. What type of distribution is this? It's geometric, right? Notice that the student's answering randomly, so the probability of success is staying the same every single time, right? What is the probability of success for this student if they're just answering these questions randomly? 0.2, right? Okay. So for our geometric distribution then, pardon me, for your geometric distribution, remember that x is counting the number of questions until the first one is right. In that case, saying until the first success actually makes sense, right? Unless your goal is to bomb the ever-loving crap out of the test. I'm guessing that your success is getting it correct. Okay? So, remember what your PMF is for a geometric? Just to remind. Times P, right? Agree with that? Okay. So in this case, then, we want f of what? Are we plugging in for x? 4? Good. And you just told me a p was 0.2, so there's 1 out of 5 chance that they're going to get it right. So we'll get 0.8 cubed times 0.2. Right? Is that okay? I think it's 0.1024. I did the arithmetic right in my head. Trace checking me. Hey, look at that. Say it again. Why is it not 5 minus 1? Because we're trying to get the fourth question. The answer is 4 here. Yeah, we're going to stop when we get it right. Yep. Okay. So what if the problem asked you instead of the first question answered correctly was the fourth question? What if you were asked that the third question answered correctly is the ninth question? This should also look like a type of problem that we've asked before, right? This is still have the same probability of success. It's 0.2 every single time, right? But we know something has to occur on the ninth question, right? In the previous 8, what has to happen? 2 be right and 6 be wrong, right? Do you know the order necessarily? No. If you knew the order, then what would your probability be? Without worrying about the order to start with. We'll fix the order here in a second. If, say, you did 6 incorrect and then 3 correct in a row, what would the probability be? Good. And think about how you would get that, right? It was 6 incorrect, 2 correct, and then the last one has to be correct, right? Okay. How many different ways are there to rearrange the 6 incorrects and the 2 corrects in the first 8 tries? You choose 2. Good. That's exactly right. Good. I've got 8 questions and I'm choosing where 2 of them are correct, right? Okay. So what if we're asked instead with a general question, the probability, and we're going to just do everything in general, just with probability of success is P, probability that I'll call it the rth question, is answered correctly. Oops, no, it is. The rth question answered correctly is the xth question. So the R here is number of successes. The X here is number of trials. Okay. Now again, don't worry about the 0.2 in this case. Let's just do a general P. We know again the very, very last trial has to be success, right? We're going to stop as soon as we see the last success, right? So that last one is going to be P, correct? We agree? Okay. How many other successes do you see? How many? The R to the, or the P to the R minus 1, right? There's going to be, I'm just trying to break it into pieces right now, right? So this is the last trial. I'll just label it. This is your last trial. Oops. So this is R minus 1 other successes. But what else has to happen? Not only do you have R minus 1 other successes, what else has to happen? Good. We have X trials, X total trials, R of them are successes. So X minus R of them must be failures. Now again, the way this is ordered, the way I have it written, this would be like I said before. This would be X minus R failures in a row, and then R minus 1 successes in a row. Does that have to happen that way? No, the only one that has to happen is the one on the end, right? These can get rearranged. How many ways can those get rearranged? Yeah, so the X minus 1 choose R minus 1, right? Because there's X minus 1 total trials. So if I write it this way, then this ends up being your PMF. So you get X minus 1 choose R minus 1, 1 minus P to the X minus R, and then P to the R. Right? In this case, your support has to start at R, right? To get R successes, I have to have at least R trials, correct? But then from then on, I could have anything. This is what's known as a negative binomial PMF. And next time what we'll do, number one, we'll show that this is a PMF. And at the same time, we'll talk about why we refer to it as negative binomial. We will calculate the moment generating function. And from the moment generating function, we will get the mean and the variance. Okay, we'll do it that way. So we'll do that at the beginning of class next time, and then do some more problems involving negative binomial. The reason why we call it negative binomial is going to require us to remember a little bit from calculus, in particular, Taylor series. Everybody's favorite topic from calculus. So we get to do Taylor series next time too. So I bet you're thrilled about that. All right, have a good one, everybody. I'll see you on Tuesday, unless I see you before.